Hi everybody, come back. Today we are going to see different ensembles: microcanonical ensemble, canonical ensemble, grand canonical ensemble in the quantum statistics or quantum statistical mechanics. So first we see the microcanonical ensemble. Microcanonical ensemble, we consider systems which are characterized by fixed number of particles n, fixed volume v, and the energy lying in a small interval E minus delta by 2 to E plus delta by 2, where this delta is far less than the E. So this is a microcanonical ensemble. The number of particles, volume and energy are fixed. Energy varies in a very small range. And in the microcanonical ensemble, the quantity that we are interested in is the total number of microstates. Total number of microstates accessible to the system, which is represented by gamma, which is a function of n, v, e and delta, the interval. Then in microcanonical ensemble we have a postulate, equal a priori postulate. This we have already seen in classical statistical mechanics. Equal a priori postulate says any one of these microstates is as likely to occur as any other. So the system has these many microstates, accessible microstates, and all these microstates have equal probability. Okay, that is what is meant by equal a priori probability postulate. Now, in quantum statistical mechanics, we talk in terms of the density matrix. The density matrix which we saw, which is rho mn, which is diagonal in the energy representation. We have seen in the last class what is energy representation. If we are using the eigenfunctions of the Hamiltonian as the basis, or the orthonormal set, the orthonormal basis, then in that basis this rho will be a diagonal, a matrix. So rho mn is rho n delta mn. So all off diagonal elements are 0, and these are the rho n is the diagonal element. So rho mn is rho n delta mn. And from the equal a priori postulate, it follows that rho n is 1 by gamma. This rho n is actually probability for the system to be in state phi n. Okay, we have definitions of rho mn and rho n. This is basically rho n. When we put rho mn in this mn, when m is put equal to n, we will have rho n, and this rho n is actually the ensemble average of the probability for the system to be in the state phi n of the orthonormal basis. So this rho n is 1 by gamma. So rho 1 is 1 by gamma, rho 2 is 1 by gamma, rho 3 is 1 by gamma. So all these probabilities are same, which is equal to 1 by gamma for each of the accessible states. Okay, so this is what is meant by the rho n, and this is 0 for all other states. Okay, this thing is 0 for all other states. Okay, so this is actually following from the equal a priori postulate. The thermodynamics of the system is determined by this expression S equal to k log gamma. Gamma, as I said, it is the total number of distinct accessible states. It is now computed quantum mechanically. Okay, gamma has to be now computed quantum mechanically, taking due account of the indistinguishability of particles. Okay. So this is the fundamental equation that we use in the microcanonical ensemble. We have used this in classical microcanonical ensemble. Same relation is there. The only thing is, while we calculate gamma here, it has to be calculated quantum mechanically, considering the indistinguishability of particles. Now suppose gamma is equal to 1. The total number of microstates accessible for the system is 1, and we say it is pure case. Okay, this is the pure case. Okay, so S equal to k log gamma is equal to 0 because gamma is 1, and this is the third law of thermodynamics, Nernst theorem of Nernst. Okay, the third law of thermodynamics. So this is pure case. Okay, so the total number of microstates accessible to the system is just 1. Only one microstate is there. Okay, so when we consider the ensemble, it's a group of very large number of systems which are similarly prepared systems, identical systems, but which are in different microstates. But in this case, since we are having only one microstate, every system in the ensemble is in one and the same state because other states are not there. So when we take the density matrix, there is only one diagonal element, rho n, that is non-zero, and all others are 0 because other microstates, if there, but it is not accessible. If at all it is there, it is not accessible. So only one diagonal element, rho n, that is non-zero, and that will be actually equal to unity because we know the total probability is equal to 1. So when you take since the total probability is 1, when you sum all the diagonal elements, we know we will get 1 because rho n is 1 by gamma. So if you add all the diagonal elements of the matrix, you will get 1, the total probability equal to 1. In this case, there is only one state accessible. Okay, so only one diagonal element is non-zero. Actually, that is equal to unity, while all others are 0. So this will be the form of rho mn now. Okay, only one diagonal element corresponding to the state accessible to the system, one state accessible to the system. We will have 1 there. Rest of the diagonal elements will be 0. So when you take the trace, add all the diagonal elements, you will get 1. Okay, so rho n is what? The probability that a system chosen at random from the ensemble at time t is found in the state phi n that we have seen. So this will be the form of rho mn. So if you take rho square, if you multiply rho with rho square, you will get rho itself because this is a matrix, so of diagonal elements are 0 and only one of the diagonal elements is non-zero and its value is 1. So rho square will be equal to rho. Now in a different representation, if we are taking a different representation, the pure case will correspond to this 1 by n sigma k equal to 1 1 to n, amk, akn. This is how we define the density matrix. This is the original definition of the density matrix. But here we are considering pure case, that is, there is only one microstate accessible to the system. Gamma is 1. So what that means is all systems in the ensemble are in the same microstate, the same state. Okay. So as we take the average, this is actually taking the ensemble average of this quantity. Okay, k equal to 1 to n means we are summing over all systems in the ensemble. So that will be, this will be equal to an conjugate, because this value will be same. This value will be same for all the systems. Same for all, since all values of k are now literally equivalent. Okay, so rho mn will be this, and rho square mn. If I take rho square mn, okay, this is rho mn, and I am taking rho square mn, multiplying this rho ml with rho ln. See, this L is same. The column number of this one, and this is the row number of this. Okay, so as we vary L and we sum, we get the product of the two matrices. Here the two matrices are row. Okay, so as we multiply, here we will have sigma L. This one, rho EML, is written in this form as AM AL conjugate, and rho LN is written as AL AN conjugate. Okay, by this rho MN is AM AN conjugate. So rho ML is AM AL conjugate, and rho LN is AL AN conjugate. Sigma L is here. So this can be written as AM sigma L AL conjugate AL AN. Okay, so we are actually summing over all the states, all the states. So we have this sigma L AL conjugate AL, that will be equal to 1. Okay, that will be equal to 1. So rho square Mn, since this is 1, and rho square Mn is AM conjugate AM conjugate, that is equal to rho Mn itself. So rho square Mn, that will be rho Mn. So this rho square equal to rho holds in all representations. Okay, so here we are not taking energy representation, we are taking a different representation. The basis set is different. It is not eigenfunctions of the Hamiltonian. Okay, so in that case, this will be this same result we are getting, rho square equal to rho. Okay, now we are considering the mixed state. This is gamma. Okay, this is actually gamma. So in this case, gamma is greater than 1. So what that means is there are more number of microstates accessible to the system. The density matrix in the energy representation is given by this. It is 1 by gamma for each of the accessible states. It is equal to 0 for all other states. So again, this actually comes from the equal priori probability postulate. Each of the accessible states have the same probability, so rho n is 1 by gamma. So the diagonal elements are all equal, which is equal to 1 by gamma, and off diagonal elements are actually 0. If we now change over to some other general representation, the general form of the density matrix should remain the same. Okay, the general form of the density matrix should remain the same. So in any representation, the general form of the density matrix should be of the same form. that is the off diagonal element should continue to be 0. Okay, and the diagonal element should be equal to one another. Okay, the diagonal elements are equal and the off diagonal elements are 0. So to ensure the property 1 as well as property 2, to ensure that the property 1 and property 2 are satisfied, so that the general form of the density matrix remains the same in any representation, for that we must have another postulate. We already have seen the equal a priori postulate, but we need another postulate here. That postulate is the postulate of random a priori phases. Postulate of random a priori phases for the probability amplitudes. Okay, these are the probability amplitudes AKN. Okay, so what which implies that the wave function psi k, okay, psi k is written as a superposition of the basis vectors phi n, basis functions phi n, using the amplitudes AKN. Okay, so this wave function psi k for all k, okay, psi k for all k, we know what is k, what k stands for, the different systems in the ensemble. The wave function psi k for all k is an incoherent superposition. Okay, they are incoherent because some phase will be attached with the probability amplitudes and the phase will be incoherent. Okay, they will not be in phase. So the probability amplitudes will not be in phase. They will be actually in random phase. Okay, so the probability amplitude will contain a phase factor as well, and the phase factor will be different. Actually, it will be random for the different coefficients. Okay. So what, as a consequence of this postulate, along with the postulate of equal a priori probability, the probability is same. Okay. What we are going to see is 1 by, if you take rho mn, rho mn is this, we know. This is the definition of rho mn. So that is equal to 1 by n, k summation over k equal to 1 to n, and akm is now written like this, a exponential I theta km, and this is the phase factor. Okay, the phase factor corresponding to the kth system in the nth state. Okay, and for this, as we take the conjugate, we will have a conjugate e to the power minus, because we are taking conjugate, e to the power minus I theta kn, and this is the phase factor here. Okay, and this a and a for m and n, see, for m and n, these are the different states. Their magnitudes are same. Okay, a and a conjugate are same because their magnitudes are same, because they have the same probability. This is related with probability. So whether it is m or n, the different states, there, the magnitude is same. The phase factor is different. Okay, this phase factor is only different. So here for a conjugate, I can write modulus a square. So 1 by n modulus a square, sigma k equal to 1 to n, e to the power I theta km minus theta kn. Okay, so we are now taking this 1 by n. Okay, 1 by n, sigma k equal to 1 to n. So what that means is the ensemble average. So we are taking the ensemble average of what? The difference in phase. This is actually the difference in phase. E to the power I theta km is the phase corresponding to state m, and this is the phase corresponding to the state n for the kth system, and then we are taking its ensemble average. Okay, so we have this is the ensemble average. So this term is written like this. We are taking the ensemble average of the difference in phase. Now, because of the random phases, okay, the postulate of random phases, the phases are all random. So as we sum over all the states in the, okay, all the systems in the ensemble for these two states, this average, ensemble average, that will be equal to 0 because the phases are all random. Okay, so this difference, that will be equal to 0 for m not equal to n. And for m equal to n, what happens? This will be same, the phase will be same. So this will be theta km minus theta km, that will be equal. So this will be 0. So we will have 1 here. Mean value for that is 1. So 1 we will get 1 for m equal to n. For m not equal to n, you are going to get this quantity, this ensemble average as equal to 0 because of the random phases. So in microcanonical ensemble, in classical statistical mechanics, we had only one postulate, which is the postulate of equal a priori probability. But here we have two postulates. In addition to equal a priori probability, which is this, rho n is 1 by gamma for each of the accessible states. Okay, and it is equal to 0 for otherwise, for all other states. Okay, so for accessible states it is 1 by gamma, it is 0 for otherwise. So this is equal a priori probability. It was there in the classical statistical mechanics. Now here, in addition to that, we need random a priori phases. Okay, where it says psi k is an incoherent superposition of the incoherent. That means the phases are all random, incoherent superposition of the states, and due to that we have rho mn is equal to c delta mn. Okay, rho mn, that is equal to c delta mn. The off diagonal elements are 0 and the diagonal elements are all equal. Okay, the diagonal elements are all equal, that is equal to c, or that is equal to 1 by gamma. Okay.